All right, so this is going to be our walkthrough for the homework assignment titled Horizontal and Vertical Tangent Lines with Implicit Equations. And this is going to be done entirely without a calculator. So the previous assignment, there was, I think, 4 or 5 of these that you had to use a calculator for. But this one, we should be able to do all without a calculator. So we'll start off by taking our derivative implicitly using the product rule, right? So for x squared y, that would be x squared dy dx, and then plus 2xy, because that's product rule for x squared y. And then we'll add to that a 2x for the x squared equals 2y dy dx for the y squared, and minus 2 dy dx for the minus 2y. Gathering all of our dy dx terms to one side, we'll gather them all to the left side, I guess, since we've already got the non-dy dx, sorry, to the right side, we've got all the non-dy dx's on the left already. When we factor out the dy dx, we've got 2y minus 2 minus x squared. So we end up with dy dx is equal to 2xy plus 2x divided by 2y minus 2 minus x squared. And since we're only being asked for when we have horizontal tangent lines, we'll start off by just setting our numerator of our derivative equal to 0. We can factor a 2x out of that, leaving us with 2x times y plus 1 equal to 0, giving us two options, one which is x equals 0 and one which is y equals -1. So first thing we'll do is we will plug y equals -1 back into our original equation. So we'll deal with the x equals 0 in a second. I'll come over here and do this. But with the y equals -1, when we plug this into our original equation, we end up with -x squared plus x squared is equal to 1, right? -1 squared is 1, plus 2. We get 0 equals 3, which we know is not true, which tells us that y equals -1 doesn't actually have any solutions in our original equation. What's actually happening here is we have a horizontal asymptote of y equals -1 for this equation. But there's no points where y is equal to -1 on the graph, so y equals -1 is not a horizontal tangent line. Then we'll go and we will plug in x equals 0. When we plug in x equals 0, we get the whole left side is just equal to 0 of our original equation. So we really just get y squared minus 2y is equal to 0. And if we factor out the y, we get y times y minus 2 is equal to 0. Or we get y equals 0, and we get y equals 2. So those are the coordinate pairs 0, 0 and 0, 2 that satisfy that equation. And if we look at both of those, those we know that those are both going to make our numerator equal to 0, but we have to check them in our denominator of our derivative to make sure that they don't make it 0 as well. And so if I plug in 0 for x and 0 for y in my denominator, we get 0 minus 2 minus 0. Well, that's not equal to 0, so y equals 0 works. And if we plug x equals 0 and y equals 2 into the denominator of the derivative, we get 4 minus 2 minus 0, which is also not 0, and therefore y equals 2 also works. So we end up with 2 horizontal tangent lines for this first one. We end up with y equals 0 and y equals 2. All right, for our next one here, 2y minus x squared y squared equals y cubed. We'll start off again by just taking the derivative. We're only looking for horizontal tangent lines again. So our derivative will be 2 dy dx. And then minus the x squared times the derivative of the y squared, which would be 2y dy dx. And then with the product rule, it'll be minus the derivative of the x squared, so minus 2x times the y squared. And that's equal to 3y squared dy dx. Solving for dy dx, I think so that I have a positive 2xy squared, I think I'll just kind of swap these two terms over. So we'll end up with a dy dx times 2 minus 2x squared y minus 3y squared on the left-hand side is just equal to 2xy squared on the right, or we end up with dy dx is equal to 2xy squared over 2 minus 2x squared y minus 3y squared. And so to figure out when we have a horizontal tangent line, we just need to set that derivative equal to 0, which really means we want the numerator to equal 0. And then we'll check those values to make sure we don't end up making the denominator 0 as well. So with 2xy squared equal to 0, I think we can pretty much right off the bat see that, if x is 0, that's going to be 0. And if y is 0, that's going to be 0. Right? So what we'll need to do is we'll need to check those in our original equation to make sure we actually get values that work. So we'll start with what I think is the easier one, which will be y equals 0. So we'll do that one on this page, and then we'll do x equals 0 on a new page. So if I plug y equals 0 into the original equation, right, for y equals 0, I end up with 0 minus 0 equals 0. Well, if 0 minus 0 equals 0, that means that no matter the value of x, I will always have a horizontal tangent line, no matter what the, no matter what x value I have, y equals 0 is always that horizontal tangent line, as long as it doesn't also make the denominator equal to 0. Well, the only thing that would make that denominator equal 0 would be if 2 minus x squared y minus 3y squared equals 0, but if y is 0, we just end up with 2 minus 0 in that denominator, which is never equal to 0. Therefore, y equals 0, which happens to be just a horizontal line that's part of this graph, is always a horizontal tangent line. Then we need to do the slightly more complicated one, which will be plug in x equals 0 to our original equation. So if I plug in x equals 0 into my original equation, right, which my original equation was 2y minus x squared y squared equals y cubed, we'll end up getting, when x is 0, we end up just getting 2y equals y cubed, or y cubed minus 2y equals 0, or y times y squared minus 2 equals 0. And that gives us a few values here. One is y equals 0, right, which we don't really need to worry about that because we've already taken care of that one with the other piece of it. And it gives us y is equal to positive or negative. I don't know why I wrote root 3 there, but it's root 2. Y equals positive or negative root 2. So we're looking at two different points. One is the point 0 root 2, and the other is the point 0 negative root 2. So what we'll do is we'll take each of those points separately. And the only thing we have left to do is to just check them in the denominator of our derivative. Well, the denominator of our derivative was 2 minus 2x squared y minus 3y squared. And so if I check those in the denominator of my derivative, I just have to confirm that they don't equal 0. So that'll be 2 minus, well, if x is 0, that whole middle term is 0. And then minus 3 times root 2 squared. Well, that's not 0. So y equals root 2 works. And if we do the same with 0 negative root 2, we're going to see it's going to be the exact same thing. It's going to be 2 minus 0 minus 3 times 2 again, which does not equal 0. So we have another horizontal tangent line of y equals negative root 2. All right, for our next one, we're going to switch it up just slightly. We're going to look for the vertical tangent lines of y cubed minus y squared equals xy. So we'll start once again with a derivative, 3y squared dy dx minus 2y dy dx is equal to x dy dx plus y when we use the product rule on x, y. So then we'll just solve for dy dx. So we have dy dx times 3y squared minus 2y minus x, when I bring this term over, is just equal to y. And we end up with dy dx is y over 3y squared minus 2y minus x. And if we're looking for vertical tangent lines, that means we need to set the denominator of our derivative equal to 0, because that was what would yield an undefined value for our derivative, and undefined slopes are vertical lines. So for this one, there's nothing nice to just factor out of it, but we can do a substitution. We can just solve for x. X is equal to 3y squared minus 2y. And if that's the case, we can just plug x equals 3y squared minus 2y back into the original equation and find all of the y values that satisfy that. And then we'll have to go back through and find the appropriate x values. So if we're going to plug in x equals 3y squared minus 2y into our original equation, which was y cubed minus y squared equals xy, we'll just end up with y cubed minus y squared equals 3y squared minus 2y times y, or y cubed minus y squared equals 3y cubed minus 2y squared. And we'll just gather everything over to that right-hand side, I suppose. So when I subtract the y cubed, that'll be 2y cubed. And when I add the y squared, that'll just be a minus y squared. And then we'll solve this, y squared times 2y minus 1 equals 0. That gives us y equals 0 and y equals 1/2. So now we'll deal with each of those separately. So if I have the a y value of 0, I can immediately eliminate that. Because what do I know about y equals 0? Whether it works in the original equation or not, which we will have to check if it wasn't a problem that we're about to see. Right? We know that if y equals 0, that means the numerator of the derivative is also 0. Right? And so if the numerator of the derivative is 0 and the denominator of the derivative is 0, well then clearly we cannot have a vertical tangent line there. It has to just be the denominator being 0. So when we do y equals 1/2, we'll now take that and plug it into our original equation. So when I put that into the original equation, right, y equals 1/2, we'll end up with 1/2 cubed, which is 1/8, minus 1/2 squared, which is 1/4, equals 1/2 of x. So really what that gives us is negative 1/8 equals 1/2 x. Or if I multiply that by 2, I get x equals negative 1/4. And so what we've got now is the point x equals negative 1/4 and y equals 1/2. Right? And if we check in dy dx, right, it does not make, right, my numerator was just y, right? Y would equal 1/2. So the numerator is not equal to 0 because the numerator was just y, and therefore x equals negative 1/4 is our vertical tangent line. All right, for number 4 here, we're again looking for a vertical tangent line. So we're going to start off just by, once again, taking the derivative. So we're going to have 1 plus dy dx minus 2x plus 2y dy dx. And then we'll use the product rule on x, y, which we've done so many times. We should just know it's x dy dx plus y, but right, it's x times the derivative of y plus y times the derivative of x. And right, when we do the derivative of y with respect to x, that's why we get the dy dx term. So we'll then go right ahead and solve for dy dx. I think I don't know, which way do we want to do this? Let's move all of the non-dy dx terms to the right, and the dy dx terms will stay on the left. So on the left, we'll have a 1 and a 2y that have a dy dx, plus this minus x from bringing this to the other side. And then it equals y plus 2x minus 1. And when we solve for dy dx, we end up with y plus 2x minus 1 over 1 plus 2y minus x. And if we want vertical tangent lines, then we just need to set 1 plus 2y minus x equal to 0, which the easiest substitution there is probably just doing x equals 1 plus 2y. So what we'll have to do is we'll have to take x equals 1 plus 2y, plug it back into our original equation, and see if we actually get any coordinate values. So if x equals 1 plus 2y, and we're plugging that into x plus y minus x squared plus y squared equals xy, our original equation, then when we plug in the 1 plus 2y for x, we get we get 1 plus 2y plus y minus x squared plus, oh, sorry, I didn't plug in the x, minus our 1 plus 2y squared plus a y squared equals 1 plus 2y times y. We'll do a bunch of distributing and combining of like terms. We got 1 plus 3y minus 1 minus 4y, and then minus 4y. That's minus, I don't know why I wrote a plus, minus 4y squared plus y squared equals y plus 2y squared. A whole bunch of bringing everything to one side. I think I'll take everything over to the right hand side just because I can see that's going to give me a positive y squared terms over there. So the 2y squared, if I add 4y squared is 6y squared, and subtract 1y squared, that's going to be 5y squared. And then I had a singular y, if I add 4y, that's going to be a 5y. And then I'm going to subtract the 3y, so that'll be a 2y, so we have 5y squared plus 2y. And the 1 and the minus 1 cancel. So we just end up with 5y squared plus 2y equals 0, which gives us y times 5y plus 2 equals 0, yielding two different possibilities, y equals 0 and y equals negative 2/5, which we'll need to then take each of those values and plug them back into our original equation to see if we get any x values. So that'll be our next step. We'll start with y equals 0. If I plug y equals 0 into the original equation, right, the original equation being x plus y minus x squared plus y squared equals xy, right, so if I put in y equals 0 for that, we just end up with x minus x squared equals 0, which gives us x equals, well, we'll factor out the x times 1 minus x equals 0, or x equals 0, x equals 1. So that's two different points. That's the point 0, 0, and it's the point 1, 0. We need to check those in our numerator of our derivative to see if they make it 0 also. If they make it 0 also, then these are not vertical tangent lines. But if they don't make that 0, then they are vertical tangent lines. So our numerator of our derivative here was y plus 2x minus 1. So we're going to now test them in y plus 2x minus 1. 0, 0, right, is going to give us negative 1. So that's that's not equal to 0, right? So that's good, right? Oh, sorry. Yeah, we're checking in the numerator. Yeah, so that's good. So that's fine. We want to then potentially use that one. And when we plug that into, or plug 1, 0 in to this, we end up with, what do we end up with? We end up with 0 plus 2 minus 1. That's just 1, right? So that one is also fine. So both of those could potentially work. Then we need to go back and test them once again in our denominator, which was 1 plus 2y minus x, just to confirm that those coordinate pairs actually solve both equations. Right? And if I plug 0, 0 into that, I end up getting 1, which is not 0. It doesn't make the denominator 0, so no. And if I plug in 1, 0, we end up getting 1 plus 0 minus 1, which does equal 0, so that's a yes. The denominator of our derivative is 0 there. So we end up getting x equals 1, but we ignore the x equals 0. So that's one half of this. Then the other half of this is going to be dealing with the y equals, what did we have? We had y equals negative 2/5. Right? So we're going to now take y equals negative 2/5 and plug that into our original equation. Right? So we're going to do y equals negative 2/5. And our original equation, once again, was x plus y minus x squared plus y squared equals xy. If I plug in negative 2/5 into that, we're going to get x minus 2/5 minus x squared, and then plus 4/25 when I square it, is equal to negative 2/5 x. And I think the best thing to do here is just to immediately multiply everything by 25. If I just multiply everything by 25, I get rid of all the fractions. So we're going to end up with 25x minus, if we multiply that by 25, we get minus 10, and then minus 25x squared plus 4 equals a negative 10x. Now it's just a quadratic. We'll get everything to one side. So we'll have a positive 25x squared. It'll be a minus 35x. And it looks like that becomes a plus 6 equal to 0 if I just get everything on one side and give ourselves a positive a value as the coefficient. With any luck, this will factor. I would guess that the best option would be a 5x and a 5x. Let's just see if we can find something that factors for this. Our options are really going to be like, we need two negatives that multiply to make 6. So that's either negative 2 and negative 3, or negative 6 and negative 1. Well, it seems to me, if I put a minus 1 and a minus 6 here, that's going to give me a negative 35x in the middle. So we end up with two x values, 1/5 and 6/5. So first thing we'll do with those points, right? Those are the 2 points that we've got here. Go to another new page here. Our 2 points that we've got here are the points 1/5 and negative 2/5, and then the point 1/5, not 1/5, 6/5, and negative 2/5. Those are the 2 points we got. If we check those both in the we'll check them both in the denominator, I guess, first. If I check them both in the denominator of that derivative, right, the denominator of my derivative was 1 plus 2y minus x. Well, if I do that with this one over here, the 1/5 and the negative 2/5, I get 1 plus a negative 2/5 times 2, so that'd be 1 minus 4/5, and then minus 1/5, which equals 0. Right? This is the denominator of my derivative. So that's good. And if I check this one, I get 1 minus 4/5 minus 6/5. Well, that does not equal 0. So this one, I'm done with. I don't have to worry about this one anymore. Right? It doesn't actually give me a vertical tangent line because it doesn't actually make the denominator 0. Then we have to check it in the numerator, right? Remembering that our numerator of our derivative was y plus 2x minus 1, to make sure that it's not equal to 0. So, well, our y value is negative 2/5, and we need to add to that 2 times 1/5, and then subtract 1. Well, that doesn't equal 0, which is a good thing. That means that this does yield us a vertical tangent line. So we have another vertical tangent line here of x equals 1/5. All right, we got a couple more here to go. This time we're asked to find both the horizontal and the vertical tangent lines. So we'll start off once again by just taking a derivative. So 2x minus 2 dy dx plus 2y dy dx is equal to 3x squared. Solving this for dy dx, we're going to factor out the dy dx from the left-hand side while bringing the 2x over there from the left to the right. So we end up with dy dx is equal to 3x squared minus 2x over 2y minus 2. So what we need to do is we need to take, for our horizontal tangent lines, we need to take our numerator and set it equal to 0. So for our horizontal tangent lines, we're going to do 3x squared minus 2x equals 0. Factor out the x and get x equals 0, x equals 2/3. We'll deal with those in a second. For our vertical tangent lines, we're just going to set 2y minus 2 equal to 0 and get y equals 1 as our possibility there. So we'll deal with the x equals 0 and the x equals 2/3 first. Those need to get plugged into our original equation to determine if we actually have points there. So let's make a new page here. If we've got x equals 0, and we plug that into our original, which our original equation was x squared minus 2y plus y squared, minus 1 equals x cubed. Right? If x equals 0, that gives us negative 2y plus y squared equals 0. I almost forgot the 1 there. Negative 2y plus y squared minus 1 equals 0. And that gives us y squared minus 2y minus 1 equals 0. That's just going to be a nice little completing the square type problem here. So we'll have y squared minus 2y equals 1. We'll need to add 1 to both sides because half of negative 2 is negative 1, and when you square negative 1, you get 1. So we add the 1 to both sides so that we can get a perfect square there. And we get y equals 1 plus or minus root 2. When we square root that, I guess I could write the steps out. We get y minus 1 equals plus or minus root 2. And you add the 1 over, and you get y equals 1 plus or minus root 2. So if you then look in your denominator, we can very clearly see that the only thing that made that 0 was when y was 1, and neither of these are y equals 1. So we have two horizontal tangent lines from x equals 0. One is 1 plus root 2, and the other is 1 minus root 2. Then we'll go in and we will test out our we'll go in and we'll test out our other value, which was, what was it? It was x equals 2/3. So if we're going to do x equals 2/3 into our original, which was x squared minus 2y plus y squared minus 1 equals x cubed, then when we plug that in, we'll get 4/9 minus 2y plus y squared minus 1 equals 2/3 cubed, which would be 8 over 27. And again, it's just a quadratic, so we end up with y squared minus 2y. And then, well, let's see here. Actually, before we do that, let's get rid of all the annoying fractions. Let's multiply everything by 27. So if we multiply the 4/9 by 27, that's going to be 12. This will be a 54y here. a 27y squared and a minus 27 is equal to 8, which is, might have been better to not do that because then we could have just completed the square, but this will be fine too. We have 27y squared minus 54y, and what do we end up with there? We have we've got a positive 12 and a negative 27, which is negative 15, and then minus another 8 is minus 23. And so once we've got that, we can just set that equal to our 0 now and use the quadratic formula on that. So we should get y is equal to the opposite of b, so 54, plus or minus the square root of negative 54 squared minus 4 times 27 times negative 23 all over 2 times 27. So lovely, nice little thing we got going here. It's now 54 plus or minus the square root of something over 54. We'll deal with that in a second. So, I don't know, negative 54 squared minus 4 times negative 23 times 27, which ends up being just plus the 4 times the 27 times the 23. Looks like that comes out to be 5,400. And 5,400 is divisible by 900, right? So we can do 900 times 6, which makes that 30 root 6. I'll go to a new page here. So really what we've got is 54 plus or minus 30 root 6 over 54. Up to you how you want to write that. You can simplify it down kind of in whatever way you want. Since there's 54 over 54 there in the beginning, I'm just going to say I've got y equals 1 plus, and then the 30 over the 54 would be 5/9, so 5 root 6 over 9, and y equals 1 minus 5 root 6 over 9. If you wanted to, you could have also said that this is 9 plus 5 root 6 over 9 and 9 minus 5 root 6 over 9, right? Same thing. So it doesn't really matter which way you go with it. So those are our horizontal tangent lines. And so we have 4 of them actually. And now we're going to go ahead and do our vertical tangent line. So we knew that it was y equals 1, but then we need to plug that into our original equation, which was x squared minus 2y plus y squared minus 1 equals x cubed, giving us x squared minus 2 plus 1 minus 1 equals x cubed, or x cubed plus x squared minus 2 is equal to 0. And of course now that's a cubic that we don't necessarily know how to factor, but we do know that using the rational root theorem, we look at the factors of the constant, which are positive or negative 1 and positive or negative 2, and the factors of the leading coefficient, which are positive or negative 1. If we divide each of those, we know that there are only 4 possibilities of what might factor nicely with this, right? It's 1 over 1 and 2 over 1, right? And just the positives or the negatives of each, so positive or negative 1 and positive or negative 2. We'll just test some of those values. I'm going to start off with negative 1. And if I do synthetic division with this, 1 for the x cubed, 1 for the x squared, 0, because it's 0x, and negative 2, I'm going to find that this one is the one that actually works. I'm going to get a 0 here at the very end. If I bring down the 1, that's a 1. Multiply the number below the line by what's in the box for synthetic division. 2 numbers above means add. A number below means multiply. Now that I'm looking at this, I think I've messed this up slightly. Let's go back a second here. This is not x cubed plus x squared minus 2. This is x cubed minus x squared minus 2, which means this is actually a negative 1 here. It doesn't affect what our values were, but it does mess up our synthetic division here. So negative 1 plus negative 1 is negative 2. Right? And then negative 2 times negative 1 is positive 2. 0 and 2 is 2. 2 times the negative 1 in the box is a negative 2. Yeah, and this should have worked, and I messed that up too. That's a positive 2, right? So that should have been a positive 2 here. That's unfortunate, but that's okay. Yeah, I don't know what I did here solving this, but this should be x cubed minus the x squared and plus the 2. So now when I have the 2 and the negative 2 here, I end up getting a 0. So sorry about that. I'm just, I don't know, going too fast over here with my little cubic equation. So we got that fixed now. We could see that it does divide nicely by negative 1, which means that this factors into x plus 1 and x squared from the 1x squared minus a 2x plus a 2. This gives us x equals negative 1. And this one, if you evaluate the discriminant, right, the inside part of the quadratic formula there, b squared minus 4ac, you end up getting 4 minus 4 times 2 times 1. Those should be flipped really if it's ac. But that's a negative number, right? It's 4 minus 8. That's negative 4, which means this has no real solutions. So the only solution we actually get is x equals negative 1. So the only thing that's left is to confirm that that doesn't make the numerator of our derivative also equal to 0. Well, the good news is, way back when we started this problem, we found all the x values that made our numerator 0, and negative 1 was not one of them. Therefore, we do have a vertical tangent line of x equals negative 1. All right, we've got one last problem here to go. Right? Horizontal and vertical tangent lines for 4x plus y squared equals 4x cubed. So we'll take our derivative 4 plus 2y dy dx equals 12x squared. Kind of a nicer one here. I think we could probably do this all in one little step. Dy dx is going to be the 12x squared minus 4. And then we got to divide that by the 2y, which will simplify if we divide everything by 2 into 6x squared minus 2 over y. So two different things to do here. One is to set the numerator equal to 0 for the horizontal tangent lines. Right, so if 6x squared minus 2 equals 0, x squared would be 1/3, right, 2/6 or 1/3, and x would be plus or minus root 1/3. So we'll deal with those in a minute. For our vertical tangent line, we'll just set the denominator equal to 0, y equals 0. That one should be pretty quick and easy. If we take y equals 0 and plug it back into the original equation, right, 4x equals 4x cubed, and then solve that. 4x cubed minus 4x equals 0, factoring the 4x out, we get x equals 0 and x equals plus or minus 1. So there's definitely values that work there. And then we just need to confirm that, we know that those all make the denominator equal to 0. We just need to confirm that they don't make the numerator equal to 0. And we know that they don't make the numerator equal to 0 because the only things that make the numerator equal to 0 are plus or minus root 1/3. So we really end up with 3 vertical tangent lines real quickly here. X equals 0, x equals 1, and x equals negative 1. Then we'll go through and we will deal with our horizontal tangent lines. So we're going to plug in root 1/3 and negative root 1/3 into our original equation. So we'll start with x equals root 1/3. If I plug that into my original equation, remembering that my original was 4x plus y squared equals 4x cubed. And if I plug in root 1/3, I get 4 root 1/3 plus y squared equals 4 times root 1/3 cubed. All right. Well, if I look at that, if I if I take those values there, I can kind of like simplify stuff down a little bit. I've got y squared equals 4 times, because these are both being multiplied by 4. Right? It's 4 times the 1, the square root of 1, and then 1 cubed is just 1. But in the denominator, it's the square root of 3 cubed, which would be 3 root 3. And I'm subtracting from that just this 1 over the square root of 3. And I think if I look at that, I can see that 1 over 3 root 3 minus 1 over root 3, right? This denominator here is bigger, which means this fraction is a smaller number. So if I'm taking a smaller number minus a bigger number, this thing inside of here is negative. Right? And if the thing inside of there is negative, right, and I have y squared equals a negative, well, that has no real solutions. So x equals square root of 1/3 doesn't yield us any actual solutions in our original equation. So halfway there. Now we'll do this with x equals negative root 1/3. Again, into our original equation of 4x plus y squared equals 4x cubed, giving us, when we plug that in, a negative 4 root 1/3 plus our y squared equals a 4 times a negative root 1/3 being cubed. And so this time this is going to work out a little bit more nicely. Let's just simplify this down a little bit first. This is negative 4 times root 1, which is just 1, over root 3 plus y squared. And then on this side, it's going to be a negative 4, because the negative is going to stay. The root 1 is 1, and cubed is 1. So 4 times negative 1 is negative 4, over 3 root 3. If I get a common denominator here, right, just multiply that by 3 over 3, we're going to end up with y squared equals negative 4 over 3 root 3 plus 12 over 3 root 3, which gives us y squared equals 8 over 3 root 3, which when I square root is going to give me two different answers. Y equals the square root of 8 over 3 root 3, and y equals the opposite of the square root of 8 over 3 root 3. And because we knew from our original solving that the only thing that made our denominator equal to 0 was when y was 0, I know that neither of those are going to make the denominator equal to 0, and those are going to be my two horizontal tangent lines. And that's the end of our walkthrough here for the horizontal and vertical tangent lines with implicit equations homework without a calculator. So you can definitely expect to see a question or two like these on your test. They're a little bit time consuming, but if you follow the steps that we need to take, they shouldn't be too horrible. And that's it.